Okay, so we're recording the old stats lesson. Okay, so a two-sample hypothesis test with independent samples. Okay, so again, your null hypothesis H0 is always something that has an equal sign, right? Mu equals something. Mu is less than something, greater than something, right? And then your H alternative is always the very opposite of that. So it's mu does not equal that same thing, right? So let's go A, call this B, and call this C. So mu does not equal A, or mu is strictly greater than B, or mu is less than C. Does that make sense? It's all just the exact opposite, okay? So H0, okay, this is the careful thing. H0 always has the equals. Now, even if you're making a hypothesis of, something is strictly less than, okay, what you would do is you would write, H0 mu is greater than or equal to something, and H alternative would be mu is less than something, right? And then you would write in the back of it, claim, right? Because that's what you're trying to prove, is that you're trying to prove the alternative. So what you want to get to, hopefully, is you work through all your stuff and you get down to where you can reject H0, thereby accepting your alternative. Does that make sense to everybody? Okay, so let's go and do a couple of these here. Okay, so again, H0, this is just kind of everything I just said on the last screen, but I want to make sure that we got it. So H0, mu1 and mu2 are the same. So alternative would be that mu1 is not mu2. So now remember, this is a two-tailed test, right? Remember, that's the one that has pieces on both sides, okay? And then H0 would be mu1 less than or equal to mu2. So that's a left-tailed, okay, because you're trying to show it less than something. And then you have the right-tailed. You with me? Okay. So here's an example. Two samples Z-test for the difference between means. A credit card watchdog group claims there's a difference in the mean credit card debts of people in California and Florida. The results of a random survey of 250 people from each state are shown on the left. That's these guys down here. Okay. The two samples are independent. Assume that sigma 1, okay, is $960 for California, and sigma 2 is $845 for Florida. So that's their standard deviation, right? Do the results support the group's claim? Use alpha equals 0.05. Okay. So let's look real quick. Claims that there is a difference. Okay. So that means we're going to have an H0 of U1 and U2 are the same. Okay. So that's what they have right down here. Okay. And you'll notice their claim is that they're different. So they're going to put H sub A as U1 does not equal U2. Can everybody read that, or is it too small?
Looks good here.
Is it okay? All right, good. I want to make sure. Yeah, I hope you're not doing this on your phone because it's really, really tiny on your phone. If you're on at least a computer, it helps. Okay, so what they're trying to prove is we're hoping to get down to where we can reject H0, right? We want to reject H0 because we want our claim to be true. Does that make sense to everybody? Okay, so now, as I said before, okay, this is a two-tailed test because we have equals. Okay, so now we look at this, we say, okay, sigma 1 and sigma 2 are known, the sample sizes are random and independent, and N1 and N2 are at least 30. So they're at least 30, right? So we're good to go, right? Okay, so we can use all of our normal stuff. Okay, so we want our level of significance to be 0.05. Okay? So remember, 0.05 means that 2.5% is on each end. Does that make sense? Because this means that 95% is in the middle, right? And there's 2.5% on the left side and 2.5% on the right. So if we go over here, turn on, come on, and I go second dister, and I go inverse normal, and I want 2.5%, right? 0.02, oops, missed the 0. 0.0, crappers. 0.025, right? I should get that negative whatever they had, right? Minus 1.95996. So that rounds to negative 1.96. And you know they're opposite, right? So if I do second dister number 3 and I put 0.975, right, I'll get the positive value of that. So the positive 1.96. Is everybody good on that? Okay. So we have to use the z-test. Let me clean this so we can see a little bit better what we got. So we're going to use the z-test. Now, remember, we claimed that mu1 and mu2 are the same. So that guy is 0, thank goodness, right? So we test our means, okay? We check the difference in our means. So 3,090 minus 2,910, okay? And then we put it over, remember that goofy sigma? The way we figure out the error, that little error right there, that whole square root of stuff. So we square root 960, which is our sigma, over how many people? 250 from each state. So that's why that goes right in here. And then the California was 845. Oh, wait, I'm sorry. Undo. And 845 for Florida. So we put our 845 squared there, still over 250, and we get 1.85. Now, let's think about this a minute, okay? We had 1.96, and we had minus 1.96, and my number's at 1.85. Well, that's only right here, okay? So I cannot reject the null hypothesis because I'm not in the reject region, am I? I'd have to be over here or over here to reject. Does that make sense? So since my 1.85 is not in that, I don't get to reject. Okay, so their drawing is a little nicer than mine. Let me see if I can make this so you can read it. Make that a little smaller. So this says, and then they point up here and there's a little orange dot, okay? So it's just a little bit off, okay? So Z is not in the rejection region. You fail to reject the null hypothesis, which means that we cannot support their claim of it being different. Does that make sense? I know there's a whole lot of negatives in that statement, right? So since we're not in the rejection region, we have to go, nope, I cannot reject the statement that the mean is the same, right? So in other words, your claim, I don't have enough information to go with that claim. Okay? Now, if we do it all in the calculator, okay, let me move this down so it's out of the way a little bit. Again, we do inverse norm of 0.05 over 2, right? I wouldn't even have had to figure out that it's 0.025. I can just put 0.05 over 2. Gives me my minus 1.96. That's where I got that. And of course, you get the same thing on the opposite side, right? Now, we're testing a 2-sample z-test. So what I end up getting is this 1.85 right there. Okay, so if you're doing the z-test, you got to go to stat test. So let me pull up my calculator, right? So I go stat tests, and I go 2-sample z-test, which is number 3. Okay, and I want to use stats because that's what was given. Okay, I arrow down. Sigma 1, right, was 960, and sigma 2 was 845, and 3060 was my debt, and 250 people, and 2910 was my debt, and again 250 people, right? And I want to test not equal, right? You can choose either one of these if you want, right? But I'm checking not equal, okay? And I go calculate, and there's my 1.85 that I got. Okay? Is everybody good on that? So once you know that this number here, right, that z number, we check it against our z that we computed from up here, okay? And we're not in the rejection region. Is that good, everybody? We can see how to do that on the calculator. It's really kind of nice, right? It's kind of fast. I mean, you can do all the stuff here, right? You could, well, let me clean that up so you can actually see it, but you can do all the stuff using this equation, right, for your z, but it's kind of hairy, isn't it? You know, just getting it in the calculator is kind of a trick, okay? Like if I was going to put that in the calculator, I mean, my goodness. Let's see, I would do parenthesis 3060 minus 2910, close parenthesis, minus 0, I'm not going to bother with that, divided by. Now, I've got a square root, and now I got a whole bunch of crap. So I've got parenthesis 960 squared divided by 250. I'm doing it this way so you can see what we have, right? We don't actually need the parentheses, but I want you to see where I'm getting all my numbers. 845. Oops, dang it, I forgot to put the parentheses in there. So if I second insert a parenthesis, now it's in there. 845 squared divided by 250, and close that parenthesis and arrow over. Now I should be able to see my number of 1.85, which is exactly what I have down there. Okay, so you can do it, right? You can do it in steps, okay? I'm totally cool with you doing 3060 minus 2910 and getting that number and writing it down. And then going, oh, okay, let me see, 960 squared divided by 250 and getting that number, and then doing 845 squared divided by 250, right? And getting that, and then going arrowing up and going that plus that, and getting a number, and then second square root, second the negative sign for my answer, right? And then arrowing back up here to where you subtracted, got 150 divided by that guy, right? And you still get your 1.85, right? If you want to do it in pieces, you can do it in pieces. However you can do it and not have it mess up, okay? I'm just saying there's lots of ways to do it, okay? If your stuff in the calculator doesn't show up exactly perfect, You know, like say your thing right here gave you 1.8, 6 or something like that, something close. That's not going to cause you to reject or accept. You know what I mean? It could be off a little bit. It's still not going to make it a whole lot of difference. Okay. Now, if you got that Z was 5.8 and it's really supposed to be 1.85, then we got a problem, right? You wouldn't want that. But if you were off just a little bit, like 1.86 or even a 1.9, something like that, at least you're going to be close enough to be able to tell. Okay? Everybody feel good? All right. Yeah. So I couldn't get the silly book to work, the e-text. It wouldn't work for some reason. So I just went through and actually did a problem out of the work section. Okay, so we can all see like how to hit these. So this is, I think, an 8.2 because I tried to do this part and the e-text wouldn't launch. It kept saying unauthorized. Do you guys ever get that when you go to the e-text?
Yes.
Okay, I don't know what causes it. I thought that it was, something when I was here at school, that it was our settings. I tried it at home and sometimes it'll fail at home. Sometimes it works. I don't know. It's not very much fun, but we just got to do the best we can. I haven't noticed any problems with like doing the homework or doing the tests or anything like that. It seems like it launches that. It's just the e-text is sometimes flaky. Okay. Now the good thing is, instead of up where the e-text is, you can always go in and look at examples. Okay. They've got videos and stuff talking about these things. So I did use that for one section when I couldn't get anything either. Okay. So let's do this one real quick. An energy company wants to choose between two regions in the state to install energy-producing wind turbines. A researcher claims the wind speed in region A is less than the wind speed in region B. To test the regions, the average wind speed is calculated for 60 days. So we've got 60 days. So that's good, right? Because we're more than 30, greater than 30. So we can use all our tests, right? The mean wind speed in region A is 13.8 miles per hour. There's a decimal in there. And a population deviation of 2.9. The mean wind speed in region B is 15.2. I'll put a decimal there for you. Okay, assume the population deviation is 3.2 miles an hour. Okay, at alpha equals 0.05, can a company's researcher support the claim? Okay, so what is the claim? Well, look back up. A researcher claims the wind speed in A is less than the wind speed in B. Oops. I accidentally dragged my sleeve. Okay, I accidentally dragged my sleeve. So it claims that the wind speed is less than the wind speed in B. So H sub alternate is that wind sub A is less than wind sub B, right? That's the claim. So that means that H sub 0 is that the wind in A is greater than or equal to the wind of B. Does that make sense to everybody? Okay, because the H sub 0 always has the equal sign. So since they said less than, we know that we've got to use the less than sign for the claim, which means that the claim is the wind speed in A is less than the wind speed in B. Okay? So our H0 is, again, the greater than or equal, and H alternative, which is our claim, is that H mu sub 1 is less than mu sub 2. That's our claim. Okay? Now, let's move on. So I know that I need 0.05, right? So that means that I need to go C, because I'm doing less than, right? So I'm going to use 0.05. If I was doing greater than, I would use 0.95. Is everybody good on that? Right? So 0.05 gives me that minus 1.645, which you'll notice my number has to round to 1.645, right? Because they want it 3 decimal places, okay? So my rejection region, because I'm less than, right, is everything less than negative 1.645, okay? Instead of being greater than, okay? Because it's a left tail test. All right. Next, the standardized test statistic can be found using technology or the formula below. So basically, it's the same formula we just had, right? So we take our stats, which if we go back, are 13.8 and 15.2. One more. 13.8 minus 15.2, which is minus 1.4. Okay? Our sigma we got from, again, the 2.9 and the 3.2 and the 60 days. Okay? Oh, what happened there? Going the wrong way here. Dang it. Just a second here. Let me clean this up. I'm looking at the board while I'm trying to push my right buttons. So I put in my, what was it, 3.2 and 2.9? That sound right? 3.2 and 2.9 or whatever it was. And then these were both 60. Okay? And we get sigma equals 0.5575. Okay? So that gives me a z of minus 2.5111. Okay? So if I remember, my thing is minus 1.645, right? Minus 1.645. And my number is way over here at minus 2.5111. Okay? So this is definitely in the reject H0. So we go back over. Remember, H0 said that the wind in A was bigger than the wind in B. But we have rejecting that, so we have to support the researchers' claim that the region A is less than the wind speed in region B. So since we reject H0, so mu A is greater than or equal to mu B is a reject, right? Then that means that mu A has to be less than mu B. That's why we accept the researcher's claim. Everybody see how you do that? Yay, nay, maybe?
Yes.
Okay.
Can you do that part one more time?
Yep. Okay, so once you get we already know our sigma, minus 1.645. So I'm going to attempt to draw this nicely. And I very rarely do. But it looks something like that, right? Now, minus 1.645 is my z part that I want to look at, okay? Everything over here is you would accept h sub 0. Everything over here, you will reject h sub 0, right? So we got minus 2.5, which is way the heck over here. So we're in the reject the region, okay? So that's why we reject H0. In other words, go back, what was H0? Oops, sorry. H0 was that the wind speed in part A was greater than or equal to the wind speed in B. And that's not what we have. So since we reject H0, then there is enough evidence to support the researcher's claim that the speed in region A is less than the speed in region B. Cool? Is it a pain in the behind? A little bit. Is it impossible? No, because thank God you got a calculator. Even if you can't use all the cool little buttons on your calculator, you still can do these, right? You notice these are all a lot the same, right? Even though we change our tests, the actual formulas are very, very similar, okay? So once you have those written down, you're in pretty good shape, okay? So if I want to do a two-sample z-test, I can go in, remember I go to second dister, and I go down to two-sample z-test. I put in my two sigmas, 2.9 and 3.2, and 13.8 with 60 days, 15.2 with 60 days, right? And then I went down, what I did on this guy here, the screen ran out of room, so I moved down so that I can see my less than U2, less than mu sub 2, okay? So that I have the right test. So when I do that, I get that minus 2.5111, which we know is way to the left of minus 1.96. So we reject H0 and we support the claim that the wind is less in region A. Okay? Everybody good? Yes, no, maybe?
It's the wording at the end that I'm getting a little bit confused on, having to figure out the difference between there is enough evidence to support the claim or there's not enough evidence to reject the claim.
Right. Okay, so let's go back.
I get the answer.
What's
I
that?
get the numbers.
You can get the numbers, you just don't know how to say the answer?
Yeah.
Yep, I understand. All right, let's start over. We'll do this again. We got time. Okay. So the researcher says that the wind speed in A is less than the wind speed in B. Okay, so the claim is H sub alternative, which is that mu sub A is less than mu sub B. That's my claim, right? Which,
because it says less than.
yes. The other one, the original H sub 0, we always use H sub 0 and we check accept or reject H sub 0. Okay? So H sub 0 has to be the opposite of H sub A. So this has to be that mu sub A is greater than or equal to mu sub B. Okay? So having this, right? Having that, I know it's a left tail. Okay? So my claim, just take it right out of the thing. What's boxed up on top, that right there is that. Okay? And we go down here and we have that H sub 0 says mu A is greater than or equal to, and then H sub alternative is the less than. So what we're hoping, right? We're hoping that we reject H sub 0. Therefore, H sub alternative is good. Does that make sense?
Yes.
Okay. So we go over here and we play with all our numbers, right? So first we do the old 0.05, right? And we get our number, 1.645. Yay. Now, I know that I want to see, am I to the left of that? Okay? So whatever number you get, okay? If you get a negative number, right? Negative, who cares, right? Then you're always looking for some number, your number, you are less than star, right? If you have some value that's a positive of star, then you're looking for you to be greater than star over there. Does that make sense? So if your number is negative, you're always going to try to be less than to reject. If your number is positive, you're going to look for something greater than that number. So you want the numbers to be further away from 0 than your z-value that came out of the calculator. Okay? So we're always trying to get outside that. Okay? So now we do all our money, right? Do all our work with the numbers they gave us. This is just a given, right? We're always going to do something like that. Okay? Because we're always trying to find that number, that boundary of where we accept or reject. Okay? When we go over here, now we use the formulas. So this just goes to 0 because our H0, remember, is what? That the two are the same, right? That's the equals part. Okay? Oops, where'd I go? Am I going the wrong way? Heck yeah, I did, didn't I? What did I do? There I am. Okay? So I come over here and now just plug in your values, right? So plug in your two values, right? 13.8 minus 15.2 is negative 1.4. Because X1, that's region A, and X2 is region B. Okay? And then we go and we put in all of our values here, 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 and here. Luckily, those two are the same, which is nice, right? But that ends up giving us the sigma. Then we just put minus 1.4 over the 0.55, and you get your minus 2.51. So then you look back at, you had what, 1.64? 1.645? Right? Once I round that, okay? And then my number, minus 2, okay? So this is it is in the reject region. So, reject. Oh, by the way, in case you haven't noticed, I'm left-handed. That's why I write so bad. So I'm claiming that as a disability. So I apologize for my handwriting. I know it's terrible. So reject H sub 0, which says that mu sub A is greater than or equal to mu sub B. Thus, we accept H sub A, which says that mu of A is less than mu of B, which is what it says right there. You all right?
So if we reject HO, there's always enough evidence to support the claim.
If this was, because this was the claim. This was the claim to begin with. Okay? So if you reject it, then you can support the claim. If the claim had been the H0 and you had to reject, then you would say there's not enough evidence to support the claim. Right? It depends on how it's worded. Right? Because this example had that H sub A was the less than, then rejecting the H sub 0 is good for us. Okay? If the claim had been the H sub 0 and we had to reject it, then we have to say that we fail to have enough to support it. See how it's a lot of double negative stuff. It really feels, it's hard to make sure we get that. Okay? How do we feel about this? Better?
Sketchy.
Sketchy. I understand. I completely understand. It's not an easy thing to grasp onto. But once it finally clicks, you'll be like, oh, that's so easy. Right? It's just like everything else math. Once you see how it's done, then you're like, oh, that's so easy. Everything is easy once you know how to do it. Okay? So let's see if we can kind of go on with some more. So we see all of our numbers. So now, 8.2. Let's do a t-test to compare means in two samples. Okay? So we're going to use a t-test. All right. So this is part that I could not get to come up. Okay. So I had to use the video of a problem. I couldn't get the dang thing to come up at the time I was trying to do this. And I needed to get some stuff done for you guys. So this is out of the video. There's a real nice lady that does these videos that you can watch her videos. They're about 5 or 10 minutes. Okay. So conditions for a t-test. Okay. Samples must be randomly selected. Ooh, that sticks out nice, doesn't it? Okay, they must be randomly selected, which they always are, right? Now, the samples must be independent, right? Okay, and each population must have a normal distribution. Okay, so in other words, you pretty much need 30 units, or they need to tell you that it has a normal distribution. One of the two, right? You need a sample size of 30, or they tell you it's a normal distribution. Okay, usually they'll tell you, okay, but just in case. Okay, so a two-sample t-test is used to test the difference between two population means. So mu sub 1, mean 1, and mean 2, when independent samples are randomly selected from normally distributed populations. So we're trying to figure out how they differ. Okay, so let's do a little work. Now, the t-statistic, okay, is still this same deal, right? Remember the one for the other variable, you had this was still there, and then these were basically go to 0 in our old ones. Remember that? Okay, now the value of S of x1 minus x2, that's the only part that's different. So you're going to have to write this down. Okay, depends on whether the population variances are equal or not. Okay, so if the population variances are equal, okay, then you create a pooled estimate of the standard deviation. So you need to take the number of samples minus 1 times S sub 1 squared. The number of samples of number 2 minus 1 times S sub 2 squared. And then you need to add up the number of samples and subtract 2. Because remember that degrees of freedom thing? Well, since we have two things, instead of n minus 1, it's an n and another n minus 2. So it's basically n1 minus 1 and n2 minus 1. So it simplifies to n1 plus n2 minus 2. Then the standard error, the standard error is then that we just computed, this big hairy thing, times the square root of 1 over n1 plus 1 over n2. And the degrees of freedom, obviously, is n1 plus n2 minus 2. So population variances are not equal. It's a lot simpler, okay? You'll notice if they are equal, it's big and hairy, okay? If they're not equal, it's a little bit faster. It's more like the one we had before, right? So it's the S1 squared, S2 squared. That's our old sigma that we had. And over n1 and n2, okay? Now, the degrees of freedom is the smaller of n1 minus 1 and n2 minus 1, whichever is smaller, okay? So let's see. Let's do a problem with it, okay? So the annual earnings of 15 people with a high school diploma and 12 people with a bachelor's degree or higher is shown below. Okay, so X bar 1 is 27,136. X bar 2 is 34,329. The sample variance on the high school diplomas is $2,318. The sample variance on the bachelor's degree is $4,962. And N1 is 15, N2 is 12. So let's go back a minute. Sample variances are equal. Sample variances are not equal. Are the sample variances equal? No. So I get to use the easy one. Yay! Okay, it's really, really rare. Think about it. It's really rare for the sample variances to be the same. I mean, think about it. If you're just taking two wildly different sets of people and going, okay, let's do this, figure out our variances, and they end up being the same, you're like, how the hell did that happen? You know what I mean? it's not very likely that they would be the same. Okay? So most likely you're going to be using this formula. Thank goodness, right? It's a lot easier. So they're not the same. Okay? So can you conclude there's a difference in the mean annual earnings based on a level of education? Okay? So use alpha equals 0.01. Assume the populations are normally distributed and the population variances are not equal. Well, obviously they aren't. We know that, right? Okay. So we want to find out, are they the same? So our H sub 0 is they are the same, right? Is everybody with me? If you're trying to find out, is there a difference, your H0 has to be, there is no difference, okay? And therefore, your claim that you're trying to see is that they're not the same. Now, since we're doing the equals, remember, this is a two-tailed because we're doing equals, okay? So we go over and we look in the T-chart for degrees of freedom. How many people did we have? 15 and 12. So we use 12 minus 1, which is 11, okay? So we look up our two-tailed test, alpha equals 0.01. I think I had that in, did I put it in here? I don't think I did. I think I had it on the last set of slides, didn't I? With that little chart? I think I did. Let me see. Trying to remember where that is. You guys remember that big chart I gave you? It was in here. I didn't take a picture of it. I thought it was in here. Where's that chart? Where's that chart? Come on. I thought I had a chart here. Do you guys remember me putting that chart in?
Yeah, I think we do have it.
Where the hell is it? Dang it. I thought that I had it in those notes. Apparently not. You might have to Google that. I don't. It's in one of the. I thought I stuck it. Maybe I stuck it in here. Hang on. Let me look. I thought I gave you a picture of that. No, I didn't. I'm a slacker. Sorry, folks. Anyway, if we wanted to go a t-test, we could Google that, right? You can Google it and find a chart real quick. Let's see. T-test table. That's what I want. So let's see. Two-tailed. So I definitely want a two-tailed test. So I've got, what was my T? I got 11 degrees of freedom and 0.01. 11 degrees of freedom.
Oh, that's one of the charts that comes in the thing in the back of the textbook.
Yes. 0.01. So it's half of 0.01, which is 0.005. And we go down to 11, and you'll notice it's at, that's a little better. Okay, so notice I'm at 0.005 and 11. So it's the first first white one, see it's 3.106. Everybody got that? Somebody say yes, please.
Yes, yes.
All right, so that's your 3.106. That's where she got 3.106, is from that table. I thought we had one. I thought I gave you one or something, but I guess I'm a big loser and didn't. So anyway, your rejection region is anything. So if we draw our little chart, so I got 3.106 and I got minus 3.106. And anything over here or over here, I'm going to throw out my claim. Okay? I'm going to throw out my H0. I'm going to throw out that they're the same. So I'm hoping that I get either something in here or something in here so that I can reject. So I can reject this and thereby support that there is a difference. Does that make sense? That's what I'm hoping for. Are you with me?
Yes.
Cool. All right. So since our variances are different, we get to use the easy formula. So we take our 2318, where the hell's that at? Oh, it's back here a page. 2318 and our 4962, right? 2318, 4962 over the two different numbers, and we get about 1552. So that's going to go in down here. And again, we go back 2 pages, and we get our 27.1 and our 34.3. We put those suckers in here, right? And of course, those are just, we're assuming mu1 and mu2 are the same, so we can check it out. That's why we always assume that, right? Is because then we can cross that term out. So we get minus 4.63. Well, minus 4.63 is certainly less than minus 3.106. So yay, I get to reject H sub 0 that says that the salary is the same. Right? Which means that my claim of that their difference is good. Does that make sense? So we go to the next page. Reject H0 because our minus 4.63. Her drawing is a lot nicer than mine, huh? I can't draw. First, I'm a man. Second, I'm left-handed. That's 2 strikes right there before I even get going. Okay? So I get to
That's
reject.
why you teach math.
That's why I teach math, because I don't draw. Being able to draw is not a prerequisite for this. We know what you try to mean, right? When you're drawing these, we're attempting to do the right thing. Okay. So testing the difference between proportions. Okay, so this is all that little p hat stuff. Okay, proportions. All right, so let's see. 2 sample z-test for the difference between proportions. All right, in this section you'll learn how to use a z-test to test the difference between 2 population proportions. Hang on. Let me make this just a little bit smaller so it doesn't run off the page. There we go. Okay, everybody good? All right. So learn how to use a z-test to test the difference between 2 population proportions, P1 and P2, using a sample proportion from each population. If a claim is about 2 population parameters, P1 and P2, then some possible pairs of null and alternatives are this. So it's exactly the same, right? This is just like the old mu sub 1 equals mu sub 2, except now it's a different P. It's a different thing, okay? So it's still, they're equal, they're not equal. Less than or equal to, greater than. Greater than or equal to, strictly less than, okay? So it's really the same exact kind of thing we're doing. We're just applying it, We're just applying it a little bit differently, okay? So again, you have to have random samples, duh. They have to be independent, duh. And the samples have to be large enough so that N1 times P1 is bigger than 5. Remember the old NP has to be bigger than 5 and NQ has to be bigger than 5 also? Okay?
Yes.
And N2P2 has to be bigger than 5 and N2Q2 has to be. Of course, if you get a big enough sample, if you do like 100 people, everything is good. You know what I mean? I mean, 100 people, you'd have to have a probability of less than 5%. So, that's why they always use a really big population. So that this is about the only sticking point you really ever have, right? Is making sure that those dang things are right. So let's do a quick example here. So, well, we'll give you the formulas first. You'll notice the formulas look just exactly the same. Okay? Sampling distribution for P1 minus P2, the difference between sample proportions, is a normal distribution. Let me make this smaller again so you guys can see everything. Okay? Normal distribution with a mean of P1 minus P2. A standard error is P1 Q1 over N1 plus P2 Q2 over N2. Notice you need to know the population proportions to calculate the standard error. Because the hypothesis test for P1 minus P2 is based on the assumption that P1 equals P2, you can calculate a weighted estimate using that. Okay, where X1 is N1 P1 and X2 is N2 P2. Standard error is very similar to what we've had before. Okay, it's PQ times 1 plus N1 over 1 plus N2. Okay, so let's do a couple of examples that'll start to make a little more sense. So obviously they're random, they're independent, and all of your stuff is at least 5. So a null hypothesis states, if it states P1 and P2 are the same, less than or equal to, or greater than or equal to, then P1, P2 is assumed the expression, and P1 minus P2 is equal to 0 in the preceding text. So that means that this is gone, right? This is where you all go, yay!
Yay!
Thank you. You got to know your audience, right? Kind of like that old, did you guys ever see that old game show, Match Game?
Yes.
And then they'd say, Dumb Dora was so dumb. And then he'd pause and the crowd would say, how dumb is she? Yeah, that's what I was waiting for. Something like that. So good job. You hit it right on the spot. Okay. Using a 2-sample test. Okay. Verify they're random. They gave me the same stuff 14 times. I don't know why, but I copied it anyway. Okay. So find the weighted estimate of P1. Okay. So thereby do your X1 plus X2 over N1 plus N2. Okay, Q bar is just obviously 1 minus P bar. Okay, verify that N times P bar, N times Q bar, N2 P bar, and N2 Q bar are all at least 5. State your claim mathematically. That's the whole H0 stuff. Okay, now identify your alpha. It's always given, right? It'll be like 0.01 or 0.05 or something like that. Okay. Determine the critical values. Use the table in Appendix B. Well, I don't have to do that, right? I can just use the inverse norm, okay, to determine my rejection region. Then finalize your statistic, see if you're in the region. Okay, so, all right, here we go. A study of 200 selected occupants in a passenger car and 250 selected occupants in pickup trucks shows that 91% of occupants in passenger cars and 83.2% in pickup trucks wear their seatbelts. That's good. That's pretty good, isn't it?
It is.
Should be higher, but I feel naked if I don't have mine on. I mean, really. When I was a kid, I never wore a seatbelt. Even growing up, I never wore a seatbelt. Even when I had one in the car. But now, since they're ticketing you, you get used to wearing it. And when you don't have it on, you feel naked. So there you go. All right. So at alpha equals 0.10, we want to figure out, can you reject the claim that the proportion of occupants who wear seatbelts is the same for passengers and pickups? So can you reject the claim that they're equal? Okay. So remember, H0 says that seatbelts for cars equals seatbelts for pickups, PC and PP. Okay, so let's figure out our stuff. Well, X1 and X2. Okay, So we have to figure out what is 91% of 200. Okay, so we go 0.91 times 200. Really? 0.91 times 200 gives me 182. So you'll notice that's why I have 182 right here. That's how many people wear their seatbelt, right? Out of 200. Now, we go 83.2% of 250. So 83.2% of how many? 250? Gives me my 208, which is my number right there, over 250. Are you with me? That's how I get those numbers. I got to use those percentages, right? So when I add these together, I get 390 over 450, which is about 0.866, right? It's 5 out of every 6. Okay. No, it's higher than that. It's a little higher than that. But 0.8667. Okay. So Q bar is 1 minus that. So that's why you get your 0.13. So now we got to check all of our stuff, right? So we check number sub 1 times P bar. So 200 people were chosen, 0.8667, right? And 200 people, 0.1333, then 250 people at 0.867, and 250 at 1.33. So let me move this over here so we can see what we have. So let's see. 200 times 0.86, that's going to be enough. Obviously, it's way more than 5, right? 200 times your 0.13 is way over 5. See how this is working? Oh, wait, I did times. Hold on. I need to do times. Times, sorry, my bad. It's still 26, so it's much bigger than 5, right? And then we do 250 times 0.866. And we do 250 times that 0.133, and we get 33. So all of those are good, right? Everybody's happy there. We're over 5 on everybody, so we're in good shape, okay? The claim is the proportion of occupants where seatbelts is the same between. So remember, just like we said here, there's our H0. H alternative is that cars are not equal to pickups, right? So let's look at the next page. So, where's my H0? Doesn't even say it. Did I miss a page? Well, let's look real quick. Let's see. Let's go to, what's my 10%? So 0.10, right? Now, 0.10, it's a two-tailed test, right? Because we're trying to prove equal. Everybody with me? So since it's straight equal, it's going to be a two-tailed test, which means you're going to go second dister, number 3, and you're going to put 0.05. Okay, so we get minus 1.645, which you'll notice is right there. And of course, if you put 0.95, you'll get the 1.6. Everybody good?
Yep.
Okay, that's why we want to make sure all that, this stuff here, all of this crap, right? That's why we want that to be bigger than 5, is because we want to be able to use inverse norm. Okay? So, now I got to figure out my z-score. Okay? So, I go back, and I've got 91% and 83.2. So, 91%, 83.2. Obviously, P1 minus P2 is 0. Then I use my P and my Q bar, and then 1 over 200, 1 over 250, I get 2.42, right? So think about where's 2.42. You can't read it here because it's too darn small, but it says z equals 2.42. It is in the reject region, huh? So you can reject the claim that the same number of people wear a seatbelt in pickups versus cars. Are you with me?
Yes.
Got it.
Does that make sense? So their interpretation, there is enough evidence at the 10% level to reject the claim that the proportion to wear seatbelts is the same. Okay? Yay!
Yay!
Okay. Do you see how is it starting to get a little bit easier? Is it starting to make a little more sense?
It's real easy when you do it.
Well, I know, but it's just follow all the stuff. Okay. All right. So let's look. We can do this in our calculator as well. Okay. So again, we go to stat tests. Okay. So let me pull the calculator up. I'll do it here. So second, I'm going to clear this out so you don't have anything in there. Okay. So I'm going to go stat tests, and I want the true prop z test, which is right there, number 6. Okay. Now, x sub 1, that was the 91% of 200, right? So if you don't even want to do this, watch. You can take 0.91 times 200 people, and it'll give you the 182. And then you have your 200 people. Oops, 200 people. And then the other one was, what was it? 83.2?
Mm-hmm.
0.832, I think it was 83.2 times 250. Oh my God, I remember that, which is 208. It'll do it for you. You don't even have to multiply it out. You can actually put it in here and let this do it for you. Then you do your 250. And you're wanting to see P1 and P2 aren't the same. So you calculate and you get your 2.418 right there, your Z. And of course, we go second dister 3, and we do, what were we doing? 5%? Yeah, so 0.05 gave me the negative value, which was minus 1.645. So the positive one would be positive 1.645. So we have, that's less than the 2.42. So we reject H0. Right? Yay! So you can do it in the calculator. You with me?
Yep.
All right.
Yep.
Okie dokie. Kind of fun when you can actually use something, right? Okay, let's see. A 2-sample z-test for the difference between proportions. So kind of the same deal here. We're doing our same kind of stuff here. Medical research team conducted a study to test the effect of a cholesterol-reducing medication. At the end of the study, the researchers found that of the 4,700 randomly selected subjects who took the medication, 301 died of heart disease. Okay. Of the 4,300 randomly selected subjects who took a placebo, which is a sugar pill, they think they're on this thing, but they're not really getting any medicine, 357 died. At a 0.01, can you support the claim the death rate due to heart disease is lower for those who took the medication than for those who took the placebo? Okay, so we're doing a lower, okay? So we're doing that H0, the death rate for medicine is less than, death rate is lower. Okay, so hang on. death rate of placebo, right? So our H alternative is the death rate from the medicine is less than the death rate from the placebo. This is our claim. Is everybody with me? See, they said support the claim that the death rate is lower. So that has to be my claim, is the second one. So H sub 0 is dm is greater than or equal to dp. Are you with me?
Mm-hmm.
All right?
Got it.
So now I want a 0.01, right? And I want everything on the left. Okay? So 0.01. So second dister, 3.01 gives me minus 2.33. So minus 2.33. That's my Z range. Okay? So we're going to use that later. Okay? So let's do our weighted estimate. So again, we have 301 out of 4,700 die. We have 357 out of 4,300 die, which gives us 658 out of 9,000. So that's 0.0731. So only 7% die. So that's pretty good. Okay, and that means that Q bar is 1 minus that. So 0.9269. So we're going to have to remember these two numbers. Okay, and let's go get our formulas. So we check all of our numbers. Obviously, 4,700 times 0.07 is going to be huge. 4,700 times 0.92 is even huger. 4,300, these are all good, right? So we can use our sample test. Okay, the claim is the death rate due to heart disease is lower for those who took the medicine. So this is what we said on the other page, right? Our claim was the medicine is less than the placebo. So the H0 is the alternative, right, to what our thing is. Okay, it's left-hand test, and the level of significance is 0.01. The critical value is minus 2.33, which looks sneakily familiar to minus 2.33, right? See how we get these numbers? We're using the same kind of numbers all the time. So we're using those same tests a bunch. So the rejection region is everything to the left of that, okay? So we're trying to reject, we're hoping, right? Think about this in real world. We are hoping that we can reject the idea that people are dying more often by taking a drug. Does that make sense? We want to reject that. We hope that a drug is doing them good. So we're hoping to get a reject. Okay? All right. Let me move this up just a little because I want you to be able to see this thing at the bottom. So let me clear these out. So I want you, we can see all these things, right? Okay. So we got our minus 2.33. Now, we take our numbers from the other page, right? So 301 over 4,700, which I'm pretty sure is 301 over 4,700. That's our 0.6064, right? And then I'm pretty sure that, what is it? 357 out of 4,300. 357 out of 4,300. Oops, crap. 357 out of 4,300 is our 0.083. So that's why we get, oops, whoa, I didn't want to do that. Okay, so that's where we get that number from. Okay, now our P is from the other page, our 0.07 and our 0.9269. So that's what goes right there. And then our 1 over 4,700, the sample that took the medicine and the sample that took the placebo. Okay, so we end up with minus 3.46. So if you look at your drawing, here's minus 3.46. Here is my minus 2.33. So thank goodness I get to reject that mu sub medicine is greater than or equal to mu sub placebo, right? That's good. So it shows the location of the rejection region. So because Z is in the rejection region, you reject the null hypothesis. That is that it's greater than or equal. Thereby, you can support the claim that the medicine works. Is that okay? Everybody feel all right on that?
Yep.
Okay. So there is enough evidence to support the claim the death rate due to heart disease is lower for those that took the medication. So again, here's all of our stuff, right? So inverse norm of 0.01 gives me that minus 2.33. Okay. That's right here. Then I go into stat tests, 2 prop Z test. So that gets me to this screen right here. Okay. These things is stat and tests, right? Remember, because you go stat, edit, calc, or test, go over to tests, go down to 2 prop Z test. Then we put in our 301 that died out of 4,700, 357 that died out of 4,300. Now, we want P1 to be less than P2. That's what we're hoping for, right? Okay. So we end up getting minus 3.45, which is, I think, the same thing that we had over here, isn't it? Yeah. So we got minus 3.46 as well. So we're in the rejection claim. Reject the claim of greater than or equal to, therefore support the claim of strictly less than. How's that? You starting to dig it a little bit more?
Just a little bit.
Just a little bit. Hey, that's better than none at all, right? Better than it getting worse. Okay?
Right.
All right. Now, we're on the home stretch here. This stuff is super, super easy. Okay? It's all about correlation. So we're trying to see if these, if the data that we have, if we can see how it correlates together, right? How good of a test or how good of a sampling, how do they match up? Okay, so to turn diagnostics on, we go to second 0, which pulls up the catalog function. So if I go second 0 and I start angling down, let me go over to my keyboard so I can hold the button, right? So I just arrow down until I get into the D's. Oh, there it is, diagnostics on. I hit enter. Hit enter again. Now the diagnostics is on. Okay. Now when I do my stuff, I will be able to see my correlation. Okay. Because I'll show you real quick. I'll show you the actual formula, and you'll be going, "Oh, I don't think so." Okay. All right. So definition. Actually, it's what, 6:30? Let's take a 10-minute break. Let me walk around a little bit and get a drink of water, and then I'll be right back. Okay, so let's call 10 minutes, and we will start back up because I need a break.
Okay.
My throat is getting dry from talking too much. If you could just tell me to shut up, we'll be all right.
Hello, guys.
Hello.
Is anybody actually understanding this?
A little bit.
Oh my God, I am so lost. I am overwhelmed. I am overwhelmed. Oh my God. How long have you been out of school? From high school?
I graduated high school in 1996.
And now, see, I'm way older than you. I graduated in 79. Oh,
I graduated in 1993.
1990.
Huh? Babies.
2005.
Oh God. It's too many numbers and it's so much going on. Oh my God. Boy. He explains it so well, and it's like we're just supposed to get it, but I'm not. I am so
I
not.
like him. I think he's funny.
Oh God, he is funny, yeah. But need some work with some answers. I need to figure out how to do this stuff. Oh my God. Mm. Wow. Is anybody local here in DeRidder?
Nope, I'm in Oklahoma.
Whoa.
No, I'm in Kansas.
Whoa.
Not since I left there in 2013.
Gee. Wow. Technology has us connected all over the world. Wow. How you guys, your grades, are they looking okay or is it looking kind of tough?
I'm doing pretty good right now. I would like to bring it up a little bit more, but I'm still in the A range.
Really?
Yeah, me too. Hard work, but I could still keep it up.
So what are you guys doing?
I'm in that 88 percentile.
Well, I'm right at the 7. I mean, hardly barely making the 7. I stay between 68 and 70. Oh my goodness.
With the homework assignments, if you use that show me an example
Yeah,
part
I
under
do
the help,
that.
and then you can ask for a similar question to redo it as many times as you need until you get it right.
Well, I'm doing that. That's why I'm trying to go back now and work on some more of that. But most of my grades in that are like 80s and in that area. But it's when I test, that's when I mess up. It's when I take my test.
Yeah, the testing is what's bringing mine down.
Yeah, look, because that time will be going and I'm watching the time and then I get nervous. And once I get nervous, I just get overwhelmed and I lose
Same
it.
here.
Yeah.
Test anxiety combined with MS is not a good thing.
Oh, wow. I don't know why we have to. It's so rough. It's so rough. Oh my God. Anyway, boy.
At least he's a good teacher, though. I mean, if he was like a horrible teacher, then this would be absolutely unbearable, but I like him.
Yeah, I mean, they can hold your attention as a teacher, yeah. You really do. Oh, goodness. Like I said, it's just been too many years since I've been out of school and trying to come back at this age and try to catch up. It's like, oh, God.
Yeah, when I had to do algebra last year, I thought, oh no, I haven't had to do real math in, 20 some years.
And I never did do well even in high school algebra. That was an issue for me as well. So then coming back after all these years, it's like, I just don't know.
Oh, sure. I hear you talking, then I come in and y'all quiet down. I see how you are.
No, it's not like we saw you coming. I think I just gave up and just went, oh, that's what he said. You probably just came in on that point.
All right. Okay. So let's run this down here. There's a lot of verbiage here, but the actual doing it is really easy. So a correlation is a relationship between any two variables. The data can be represented by ordered pairs, x, y, where x is the independent variable and y is the dependent variable. Okay? Obviously. Now, the fact that two variables are strongly correlated does not in itself imply a cause and effect relationship. Okay, consider the following. Is there a direct cause and effect relationship between the variable? That is, does x cause y? Is there a reverse cause and effect? Okay, that is, does y cause x? Is it possible the relationship between the variables can be caused by something else? Okay, or a combination of something else? Is it possible the relationship may be just a coincidence? Okay, now normally we just say no, it is pretty much cause and effect. So if you look, the correlation coefficient is a measure of the strength and direction of a linear relationship between two variables. The symbol R represents the sample correlation coefficient. The formula. Okay, so let's look at this a minute. First of all, you have to take your X's and Y's, right? You have to multiply each X and Y together and add them all up, right? So let's say you have 1, 2, 3, 5, 5, 9, right? You would do 1 times 2, which is 2, plus 15, plus 45, and you would multiply that by 3 because there's 3 sets here. Then you would subtract the sum of the x's, so 1 plus 3 plus 5, times the sum of the y's, which is 2 plus 5 plus 9. And then you're going to put all that over the square root of all of that crap. It's like, are you kidding me? Okay? We're not doing that. Okay? Homie does not play that. What are we going to do? We're going to use the calculator. Okay? All the way, baby. Okay? So, trying to figure out the correlation coefficient. So, determine the number of pairs in the sample. Specify the level of significance. In other words, your alpha. Okay? Find the critical value. Use table 11 in appendix B. Okay? Decide whether the correlation is significant. If your absolute value of your R that you get is greater than the correlation coefficient that you got, okay, then it's significant. Otherwise, there's not enough. Okay, so let's look. Obviously, looking at these, okay, you can tell that this is probably a pretty good negative linear correlation, right? They're pretty much all in a straight line, aren't they? Okay, whereas this guy is a positive linear correlation, which means you have a positive slope. Does that make sense? Look at this one in the bottom left. Is there any kind of correlation at all? No. This looks like if you told kindergartners to throw a dart, a whole kindergarten class. That's the kind of crap you'd get there. Okay? So there's absolutely no correlation. Does that make sense? Or if I threw a dart, you get the same thing. Now, you'll notice this guy looks like he would fit a parabola really good, wouldn't he? So he has what we call nonlinear correlation. Does that make sense?
56. He got 42 out of 56 for complete.
What's that?
What did they find?
What are we doing? Andre, do you have something else on?
Hot.
Andre, mute yourself. All right. So, a researcher conducts a study to determine whether there's a linear relationship between a person's height and pulse rate. The data is shown in the table below. Display it in a scatter plot and describe the type of correlation. Done. All right. Let's do this. So I just turned on my thing, right? My diagnostics. So I go to stat and I go to edit. So now I want to put my numbers in. So let me pull this down so that I can see them all. I got to go to my 10 keypad so I don't have to put it on the calculator. So I got 68, 72, 65, 70, 62, 75, 78, 64, and 68. Now I go to list 2. 90, 85, 88, 100, 105, 98, 70, 65, and 72. Now you'll notice my 2 lists are the same length. Okay? Thank goodness. Because if they're not, you are hosed. You missed somebody. Okay? So now we want to show this, right? So we need to set up our display. So my X's, they're between 68 and 78. So let's do 60 to 80, okay? So I go to Window, and I go 60 to 80, right? And my Y's look like they're between 65 and 105. So let's do 60 to 110. Does that sound okay? Now, if I want to see them, I have to go to second and to y equals. What is that noise in the back?
That's my cat purring, sorry.
No, it was somebody talking. All right, so second stat plot, and we hit enter, and we turn it on. Now, you'll notice it's a scatter plot. You can change those to different things, but we're not going to. Now, you'll notice that X list is L1 and Y list is L2, which is good because that's what we wanted, right? So now, if we graph this, okay, I should see my points. Is there any kind of correlation to that? Any correlation at all to these dots?
Nope.
No. No. Now, if you want to find out, you can go to stat and you can go to calc and you can go down to number 4 and you can do a regression. Now, it shows that it has a minus, so 14.6%. Okay? That sucks. That sucks bad. Okay? Pretty much if you're not at least 80, you have no correlation. Okay? And here we only have 14%. So we're going to have none. Okay? So let's look. Now, the critical values for the Pearson correlation coefficient. Okay, so let's go back to our problem. Linear relationship, blah, blah, blah. Did they want? They didn't tell me how many. Okay. Now, A26, okay, that is your page that you want to remember where it is because that's where these values are at. Okay. So bookmark that page on your e-text, or just go to that page and print them out. Or you could probably look this up online, right? Critical value for Pearson correlation table. Oh, table of critical values. So you can go in here and you can look and go, oh, look at that. There's all my numbers. Okay. So if I went over here and I looked at, where was I? How many pieces? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So I go over here. I got to come off that by 1. So 0.5, 0.6, 0.7. So clearly that's a no. Right? But you can find them anywhere you want. Okay? How I have a bug in my office, I have no idea. It's cold outside, but whatever. Just smacked him. All right. So we just simply look up this stuff on the page. So I've actually got 2 pages for you. So you have between 4 and 100. So if you bookmark these in this text or take a picture, here you go. Ready? Go ahead. Take a picture of that. If anybody wants to take a picture of the screen. I don't know if you can take a really good picture, but there's one page. And then there's another page where they basically, once you get to 30, they just jump by 5s because the numbers aren't really that different. Okay? So, the number of years out of school and the annual contribution. So what I did is I put in the numbers in L1 and L2. I did calc, len reg, and I get that it's minus 0.9078. Okay? Now, because it's close to -1, this suggests a strong negative linear correlation as the number of years out of school increases. Okay, so nostalgia wears off, right? The longer you're out of school, the less you give to your alma mater. When you first leave, you're like, oh, I love this place. I got to help give them money to keep them going. And then pretty soon you're like, I got a wife and kids and a mortgage and 3 dogs, and I can't afford to give any money to school, right? Life happens, and all of a sudden you don't feel like giving as much money. Okay? So 7 pairs using alpha equals 0.01. So let's go back to 7 pairs and alpha equals 0.01. 7 pairs, alpha equals 0.01. So that gives me 0.875. So there's my thing from the table, 0.875. So since I got 0.908, right there, 0.908, and that's bigger than my 0.875, I say there's significant correlation. You good? All right, a t-test for a correlation coefficient. In example 4, we used 10 pairs of data to find 0.874, did we? I don't know if we did or not. They claimed we did. I don't remember that problem, but whatever. So we found a correlation of 0.874. We want to test the significance at 0.05. So the null hypothesis is there's no correlation, okay? And the alternate hypothesis is there is significant correlation. Because there's 10 pairs of data, we have to go get, oh yeah, I forgot. Sorry, I messed this up over here. This I messed up. I'm supposed to take, with 7 pairs of data, I'm supposed to use 5. That's my fault. So 959. Oh, that makes a difference. $959. So my number is actually less than, gosh, I can't believe that, 959. They're claiming no significant correlation. Wow. Okay. Well, that's the way it works. All right, so let's see. We're doing P equals 0. That's not what I wanted. We're doing P equals 0, right? So remember, that means it's a 2-pair test, 2-tail test, okay? So we're wanting 0.05, and the degrees of freedom is 8. So 0.05, and the degrees of freedom are 8. So 0.834 is the number I'm looking for. So 0.834 gives me a critical value of minus 2.306. Wait a minute, what? Hang on. Hang on a second. Second, no, that's not it. Second. T-test. Stats. No, that's not what I wanted. What did I want? I'm trying to remember where I want. There it is. Inverse T. So area is 0.05. Degrees of freedom are 8. What the hell is that? How did they get... Oh, it's a 2-tail. Dang it. Sorry. 0.05 divided by 2. Now I'm going to get the number that they got, which was at 2.306. Okay. So I don't use the t-table yet. I just use the regular old inverse t. Okay. So now I got to try to figure out my R Oh, 0.874. Yeah. If I go to 10, I go to 8 with 0.05. I go back here. 8 with 0.05 is 834. That's my R, or 874. So 1 minus that over that is 5.087. Now when I look at it, I say my thing is way over here, right? And I'll have to be at least there, okay? Note the results differ slightly at rounding, so we can check that out. So 5.07, so there is correlation, okay? We reject the no correlation and we accept significant correlation. Okay, calculating a correlation coefficient. Okay, so if I'm doing that, I got to go stat, and I got to go number 4. I got to clear my lists. So I go second L1, comma, second L2. Now my lists are clean. So now when I go to stat and I edit, my lists are empty. But I did not do second plus 712, okay, because that would get would turn my diagnostics off, and I don't want to do that. So now I put in my 1.8, 1.3, 2.4, 1.5, 3.9, 2.1, oops, 2.1, 0.9, 1.4, 3, and 4.6. I go over here, 604.4, 434.2, 544, 370.4, 742.3, 340.5, 232, 262.3, 441.9, 1157.7. So again, they're the same length, but thank God, right? Now, I go to stat calc 4, and I get 0.8736. Okay? You'll notice there's my 0.8736. Now, if I want to check my stuff, okay, all I have to do is I can go to tests. That LinReg t-test. Okay, list 1, list 2, frequency 1. I want not equal. Go down and calculate. And you'll notice that my t-value is 5.07. Okay, so I know that my rejection region is anything more than 2.3 or less than minus 2.3. So I'm at 5.07, so I know that I'm going to reject. So that's a lot easier than putting all of this crap in your calculator. Okay, doing this is a whole lot easier. Okay, everybody all right with that?
Yes.
Yep.
So you got to do your linear regression first, and then you do your LinReg t-test, and that will give you your numbers. Okay, everybody good? It's pretty good. All right, so linear regression. So now finding line of best fit. So a regression line is the line that fits all your data the best. So they're trying to find a least squares method, really, is what they're doing. So they're trying to see who misses by the least. So what it does, your calculator goes and readjusts this line many, many times until it gets to a nice value. Okay? That's called the line of best fit. So in the equation for a regression is obviously y equals mx plus b. That's just a straight line. Now your slope, again, look at this thing. It looks similar to that junky one we had before, right? We don't want that. okay, we are just going to use your calculator, okay? So fitting a line of best fit. So we already did this, right? And we got our, let me go back to stat and I'll show you that real quick. I just used the same data, right? So 199.534 and then 56.0357, okay? Now, in the red, I did it in red because I want you to be very careful, okay? When you enter your data, you have to be accurate or your answers will be way, way off, okay? When I did it the first time, I put it in my calculator, and when I looked at it, my numbers were really, really screwy. I mean, they weren't even close. I was like, what the hell? So I looked, and my second entry, right, that 434.2, I had missed the 3, and I put in 44.2. Well, I mean, God, 44 in the middle of numbers that are in the hundreds is going to totally screw stuff up. Okay, so that's why. So if I got my numbers that just look funny, or I think they feel funny, go check. In fact, I would always, before you go hitting stat calc, I would go check all your data to make sure that you didn't fat finger something, because it's very, very easy to fat finger and put something in wrong. Okay? So be very careful with that. Okay? So another one on the calculator. Okay? Just messing around here. So I'm going to just go second plus 712 because I don't need my regression coefficient. I'm just trying to find the line. So now I can just go stat, edit, 1.8, 1.82, 1.9, 1.93, oops, 3, 1.98, 2.05, 2.13, 2.3, 2.37, 2.82, 3.13, 3.27, 3.65, 3.78, 3.83, 3.88, 4.1, 4.27, oops, 4.27. Good grief. Get your fingers in the right spot there, buddy. 27. That was a hard one, wasn't it? 4.27. 4.3, 4.43, 4.47, 4.53, 4.55, 4.6, and 4.63. Are there 25? Let's go count. 2, 4, 6, 8, 10, 12. 13 and 12 is 25. Okay, so I got a chance there right. Okay, let's go over here. 56, 58, 62, 56, 57, 57, 60, 57, 61, 73, 76, oops, 76, 77, 77, 79, 85, 80, 89, 90, 89, 89, 86. Man, I suck at typing tonight. 89, 86, 92, and 91. Oh my God, they're the same length. Okay, so second quit, stat calc 4, and you get 12.4809 and 33.68, right? If you want to graph this, watch carefully. This is saved. Okay, let's go to stat plot and we will turn it on. Okay, now let's go to our window. What is the lowest x? 1.8, right? So we can do 0 to what, 5, right? That should be all right. And my Y min, let's do 50 to 100 by tens. Okay, so if I graph this, there's my data. Notice I've got the data. Now I want to put the line in. Okay, go to Y equals. Are you writing this down?
Yes.
Go to Y equals. Then go to VARS, right down here, VARS, and go down to number 5. Statistics. Okay, we don't want any of those statistics. We want the equations. Number 1 is the regression equation that we just made. Okay, so if I look at it, notice it goes 12.4809. So if I'm trying to round it to a couple decimal places, I'll change that to a 1, and then I'll hit delete until I get right before the X. And then I'll go over here, 33.68, make that a 3, and then delete the rest of these until I get down to my regular thing. And now if I graph it, you'll see my line going straight through that graph. So it's stat, edit, put all your numbers in. Second, quit. Stat, calc, 4. Enter a few times and you get your line. Okay? Then you can print your line by going Y equals VARS, statistics, equations, number 1. That will give you your line. To turn on these plots, you go second Y equals, because it says stat plot right there, and you turn it on. So you'll have to hit enter twice, and it will click it from off over to on, and that will allow it to graph your data that's in there. Are you with me?
Yes.
All right.
I need that calculator.
It's handy. Okay, so predicting your Y values using regression equations. So we're going to go back and use our equation, right? So there's our Y equals 12 point, oh, different one. Okay, so let's second plus 712. Okay, so we're saying that the regression equation for the gross domestic product of carbon monoxide emissions is blah. So here's my regression, 199.535 x plus 56.036. This was for data that we did back over here. Where's that 199 at? There it is. All of this stuff that we had when we put all this in, that same information, that's what we're using right here. Okay? So I've got my thing, right? Now, I want to see what it does when I'm at x equals 1.2 and 2.0 and 2.6. So I need to make sure that I set my window. Minus 10 to 10 is probably fine. But look at these numbers. Okay? They start at 56. At 0, you're at 56. And for every 1, you're going to add 200. So I'm going to start at 0, and I'm going to go up to 1,000. Okay? So I'm going to make my window 0 to 3, because that's all I need to really go. Okay? And then I'll go from 0 to, what did I say, 500 by 100s. So now if I graph, I have my line. Okay? So normally I would have had all that information still in, but unfortunately I put a different variable in. I'm sorry about that. But I go Y equals statistics, reg equation, right? And you wind up with your value, right? So truncate it down to the number of decimal places. Now, we want the value at 1.2. So if you look above the trace, there's a thing called calculate. So I want to calculate the value, number 1, at 1.2. And I get 295 0.478. The book says 295.478. Right there matches my calculator. Okay? If I want the value at 2, I do value at 2.0, and I get my 455.106, which you can see right here. If I want 262.6, I second calculate 1 at 2.6, and I get 574.827, which is right there. So I did a screen capture of the 3 things I just did. So that's how you can identify what to expect, right? To kind of predict what's going to happen later on. Okay? So you put in all your data. So we go back here to, where was it? Was it this guy? Yeah. Put all your data in, get your regression equation. Then go to y equals vars 5, right? So we went y equals vars 5 equation, regression equation, right? And we have our stuff. And then you go second calc value, and you can put whatever value you want. So it's going to say x equals. If I wanted to know at 4.5, oh, there's a trouble. My window did not go out that big. So if I change my x to 5, and now I graph it, and I go second calc 1 at 4.5, it will work because it's got to be in the window. So that's the only thing, is make sure that when you're using this, that your window is the right size to be able to see these points. Does that make sense? Okay. That's all I got.
That was a lot.
It was a quick little 2-hour lecture. Who'd have thought? Right?
Yeah.
I know it's kind of fast, but this regression stuff is actually pretty fast. Okay, and you can use your calculator for all of it, which is nice. Okay, so please do that. If you need a regression, right? Watch. Linear regression calculator. Google it. Quick linear regression calculator. Boom. Put in your x values. Put in your y values. Right? Calculate the regression equation. So 1, 2, 3, 4, and 2, 6, 9, 11. Right? And I go down here and I go generate. Right? I get 3x minus 0.5. Okay? Oh, look at this. Look at all these cool information down here. Sum of x, sum of y, mean, sum of the squares, sum of the products, regression equation. Wow, that's cool. Okay? So you can always find that too. Now, this unfortunately doesn't look like it does the correlation. So let me see if I can go back here. Calculator with regression. I'm sorry, correlation coefficient. So now you have the same thing, right? Enter your data and boom, it will come out. Okay? So a lot of these you can find something Googled if you absolutely need it. Okay? All righty. So that's the end of that. Now, real quick, let's go up here and let's look in here. Now, Assignment manager. So all of the tests are still open until the 8th. Okay, so if you look, the 8th is next Tuesday. Okay, now the final exam has to be done by the 11th. Okay, so let me go look and see if this 240 minutes allowed. Let's see. Anything about passwords? Nope. So I'm not requiring Proctor U. I'm not requiring a password. Okay. So you can go on and you can take it. I'm not doing this either. Okay, because I don't want you hung up on that. So if your stuff gets interrupted, like you got bad internet, okay, it's not going to make you talk to me first. It'll allow you to just go back in. Okay? Yeah. I said it that way because I don't want you guys, you're going to be in full test mode. I don't want you waiting on me to go reset your test for you. Okay? So that's why I opened that up so that everybody can have that. All right? Okay. Let me go over here and let me go to more tools, attendance. What the heck is today? 30th? Okay, let me turn the light on. Okay. Oh, so this is the attendance I want to do. So today is probably in here somewhere. 11:30, right? So let's put 11:30 together. So, Andre,
Here.
Glennis. Miss Glennis was here. Regina?
I'm here.
Regina is not here, correct? Okay. Jessica Green. Not here. Mackenzie Harrington is here. Mike Leo is here. Josh is here. Aaron was here. Lonnie Price. Thought I saw Lonnie. Yep.
Here.
Stephanie Roberts. First in the door. And Terakita is also here. Right?
Yes.
So 1, 2, 3, 4, 5, 6, 7, 8, 9 people here. I have 9 people on my list. Is that everybody?
Yes.
Woohoo! Save. All right.
Yeah.
You've all got credit for being here. So, again, when you're on the doing your assignments, right? When you're looking at stuff. So let's say let's go to chapter 9, okay? And you're doing your homework. You're like, oh man, I got no idea, okay? You can always go to question help, right? You can do the textbook. You can ask my instructor, right? You can do all of that stuff, okay? So here, question help. Help me solve this, right? It'll walk you through the steps, okay? Help me solve this. It'll walk you through everything. You can view an example. You can watch a video. All of this stuff is super, super helpful because sometimes it's hard to marshal your thoughts of what you want to do on each problem. But if you do it this way, you can watch a video about it. You can look at the textbook part that talks about it, whatever, okay? So don't be shy using that. All those tools are there for a reason. They're there to help you, okay? All right.
I think the view the example, Mr. Render, is the best one because if you hit help me solve this, then it automatically counts that one wrong. But if you hit view an example, then it will show you an example of that without counting it wrong.
Oh, okay. All right. Very good. Thank you.
But you can
Online.
also do a similar question, and then you get the score for the next one you do yourself. So
Yeah,
you can
that's
always make up for your missed scores you have if you have yourself walk through it with this option.
Okay.
That's true. Yes.
All right. Now I've set all the tests that you have to have at least 20% before you can take the test. Now you probably should do a whole lot more than that, but I didn't want you to be stuck, not being able to get 20% of them right and not be able to get the test done in time. Okay. But
Okay.
I could really be mean and do 100% right. You had to do every single problem right. That would suck.
It would suck.
It would suck bad. So we won't do that. So you have to have 20%. So it's not too bad. Okay. So again, use the hints in the homeworks. Okay. And if you do still have problems, shoot me a text, or at least, let me know that you sent me and ask your professor. Because otherwise I'll never know. Okay.
And are we meeting next Monday? Did I miss something?
No, I don't. Well, there's no really reason to,
Okay.
because you guys are just going to do the test,
Okay.
right?
Yeah. How many questions is on the final exam?
I don't know. Let me go look.
Need the view example on the test.
Quizzes and
Yes,
tests.
we do.
I can't add remove content. I thought. Hang on, I got to go to.
Oh, I guess you'll just have to look at list questions.
18 questions.
On the final exam? Wow.
Can we get the view example on the test?
Yes.
No.
Mhm.
Wait a minute. Okay. Okay, so 18 problems. Or yeah, that's not too bad. Okay.
Okay.
So actually, let me go back here. That's not what I wanted.
Who's playing Call of Duty?
I don't know. Okay, so if you look at this, classifying data, section 1.2, 2.1, 2.2, 2.3, 2.5, it tells you exactly what sections you're really working on. Okay? Now the question IDs, you guys don't have access to those. You don't know what ID is what, but you can still. Okay? So estimated time is 85 minutes. Ooh, I might want to up this then.
Oh, definitely.
Oh, 85, I'm giving you 240. That's almost 3 times as much. You should be all right. Okay?
We appreciate you.
You betcha. No worries at all. I guess we'll talk. Do you guys need to get together next Monday to just kind of talk over stuff? Or
We can get together and go with the test together.
no. Good try though. I like it.
We could go over problems that would be like on the test, but not the test.
Yeah, that'd be awesome.
Oh, that'll be good.
Okay, maybe I can figure something out to do there. All right?
I'll take it.
Okay.
All right, guys. We'll talk to you next week. Then we'll go ahead and Zoom meeting next Monday at 5.
Sounds
Okay.
good.
All right.
Hey.
Bye
Bye,
bye.
everybody.
Bye.
Bye.
Bye.